Okay, Raj is here, which is great. And so, Adam, let me give you a little intro here. I know.
Can you hear me okay?
We can hear you, Raja.
Oh, good.
Welcome.
Okay. Sorry. Yeah.
No worries. Well, so Raja, first of all, you should know that audio problems are a part of this podcast, and those of you who like to send us complaints about the audio, well,
Yeah.
We know.
we know. We
Yeah,
also
exactly.
like, you know what, like, hey, you don't complain about the ads on the podcast. Don't hear you complain about
That's
that.
right.
So it's like,
That's right.
sometimes like, look,
And also,
no intro music.
we do AI generated transcripts too. So, if you don't like the audio,
Go listen to those. Yes.
yeah,
So,
go read it up.
and also, it used to be way worse. Like, go to that Showstopper episode and go to Twitter Spaces, any Twitter Space, and
Yeah.
go listen to the Flying Blind episode with the clarinet solo in the back. I mean, it's like come on, there's so many. We have come a long way.
Go to episode 1, which sounded like we were holding 2 tin cans with a string between.
Totally. Right. So we've come. So, Raja, you may be thinking to yourself, God, this podcast can't get any worse. In fact, we know it can get worse because it started much, much worse. So I would like to say that in terms of but we got some feedback. So the feedback that we often get on the podcast, well, first of all, I would say most people would say, I love the podcast. Even the baseball episode, I've heard that a couple of times. Like, you don't have to say that. Just have to qualify that.
Just leave it there, right?
Just leave it there. But a lot of positive feedback on the podcast. Then we get the audio problems set, which is like, I get it. I understand. You're upset about the audio, and fine. Sometimes those complaints are well-founded. Sometimes those complaints are a lot less well-founded. I'm sure you read all. Do you read the YouTube comments, Adam? You must read all the YouTube comments.
Yeah. I actually, they email me with every comment. I feel like
we did have a commenter who's just like, the way apparently like my de-esser is not working properly on this setup, and like the way I pronounce S's just like causes him to have a nervous breakdown. I'm so sorry. That's just not going to change. So anyway, we've started to get a little bit of new feedback that I kind of love. We've taken requests. So people asking us for subjects that they would like us to tackle on the podcast, which is not brand new. This has happened historically, but I really like this, I have to say. If people want us to there are certain topics you want us to take on, you should let us know. And because we do very poor advanced planning, you may find that our latency from your suggestion to an Oxide and Friends may be very, very low. We may have exceptional latency. So as we do in this case, so this is a listener of the podcast who is an industry analyst, so someone who follows the podcast, but is not necessarily a software engineer, but is very technically proximate and having to deal with a lot of these things. And I was sent in particular, and I'm going to drop this link into the chat, a Forbes article that this industry analyst had come across about vector databases. Which, don't worry, we're not going to talk about vector databases. This is not a pop quiz, Adam. Not that sorry, that sounded much more pointed.
I don't like I've heard of vector databases. I'm not looking on the Wikipedia article right now.
Right. But this Forbes article talked about it's trying to talk about cap trade-offs for vector databases. And in particular, there's a sentence in here that the analyst was really latching onto, which is, at this point in technical evolution, it is impossible for vector databases to guarantee all three of cost effectiveness, accuracy, and performance at the same time. So consider that vector databases are compute heavy and can run on different types of hardware. For processing, CPUs are slowest, GPUs are faster, and FPGAs and ASICs are fastest. And Raja, I'm sorry if you just threw up in your mouth a little bit. I'm just reading the text here. So I just want to be
not an endorsement.
This is not an endorsement of this. And so this analyst asks the very reasonable question of like, what are these things? I have basically not had to deal with, I've been dealing with software folks for my career. In terms of the industry, like, could you please do an Oxide and Friends that explains the difference between CPUs and GPUs and FPGAs and ASICs? That is a really good idea. And I'm like, who's the right person for that? Because you need to get someone who really understands these things really well, can speak to a bunch of these different kinds of things. And then Raja, you had this great tweet over the weekend, really interesting tweet over the weekend. And I'm like, Raja's the right person for this. So Raja Koduri has spent an entire career in silicon and has been in many different interesting places and really thinks about all these things holistically. So, Raja, I hope you don't. I think that you are the perfect person to answer this question or to take us kind of through this. And if you don't mind, I would kind of like to start with Adam, I'm going to channel some On the Metal here a little bit. On the Metal, Raja, was our podcast that we started when we first started the company. That is kind of doing these long form interviews with folks, and I want to channel that a little bit because if you don't mind, I would like to get into kind of how you got your start in silicon and in chip design, because it was on the graphics side of things, right? I mean, you started working for S3, and I often have to explain that Sun Microsystems was a computer company. I don't know how often S3 comes up in conversation for you, but you must be like, no, not the object store. No, there was a company.
Yes. Yeah. Thanks, Bryan, for inviting me to this chat. Yeah, I became a silicon person by accident, frankly. So, I got smitten by computer graphics when I was in grad school back in India. Okay. Because I saw that, hey, with math, you can draw pictures, right? And that was so fascinating, right? It was, but there weren't any computer graphics jobs. Actually, there weren't any much computer jobs back there in India, but whatever they were, were in, kind of databases and COBOL programming. If anybody knows what COBOL is, and now that's even dating, a few decades back than S3. So, I did various kind of miscellaneous stuff, and the first time I had an opportunity to come to Silicon Valley to work for a computer company called Tandem Computers. And
Tandem, I didn't know that.
Yeah. So I worked on their parallel transaction database system, and that's where I got first encounter with networking and parallel things, right? How to code things to be asynchronous parallel and all. But my kind of itch has always been computer graphics, and back in the early 90s, there were 16 graphics hardware startups in the Bay Area. Okay.
Wow,
and it was like AI back then. Okay, right? Everybody was building a 3D chip, 2D acceleration chip, 3D acceleration chip. And so applied for a job, to several companies, but because I had no background, right, other than some academic stuff, finally I got into a game developer support engineer role, right, a junior role. So I kind of, went backwards in my career. That was, blooming on the networking side to take an entry level job, and it was fun because it's like, hey, this games were super cool back then, and you get to work on helping game developers optimize the games for your hardware, right? So that kind of was my first job. So then you start working with really this, the game programmers back then, they were like geniuses, right? Because the game programmers,
this is the John Carmack era of game programming.
Exactly. John Carmack.
John Carmack, right?
Yeah. So I met John Carmack and learned a great deal from him. But I was bringing back to the hardware team, right? Hey, we need to do this. We need to do this. You need to fix this. You need to do this. You need to do. So I was the translation layer between John Carmack and my silicon designers. And and that was kind of my job. And one day, the guy, who was running the architecture team said, "Hey, you seem to be pretty good at. Why don't you join us rather than the guy who complains and constantly demeans us?" And that's the slippery slope, right? I joined the team and I said, "Oh, cool! Like I get to build the stuff." And then, here I am, almost 20. 6 years later, right? They call me Silicon Guy, but no, I was, a game developer support engineer. That's how I started before getting sick. Yeah, and stuff. So that's kind of my journey into. I came from the software side of things, even though, my undergrad is on electrical engineering, electronics, communications, and all, I kind of, wandered off into networking software in computer graphics.
Because that's where the jobs were, and then kind of bided your time. And yeah,
Yeah,
that is
yeah,
wild. And so this is a really interesting kind of era, because you said it was explosive. There were a bunch of different. I mean, I think it's a really interesting parallel of kind of the AI boom. You've got a bunch of different
yeah.
companies out there. This is like the era of 3DFX, right? I mean, I
Yes,
remember that
yes.
the
Yeah.
and Adam, have you watched that Computer History Museum
Yeah.
panel on 3DFX, which
Yeah. Really
Arian
interesting.
pointed us to, which is outstanding about the 3DFX
Yeah.
folks. Raj, have you seen this? I mean, I'm sure you would you would have very similar memories of kind of that era. And this is a
Yeah,
really,
I sometimes I see those history things, and first off, I don't like them because it makes me feel like I'm all, like I'm in the History Channel, like, and the stuff, because I grew up with all of these guys and the stuff. And to me, all of this seemed like yesterday, right?
right.
Not that long time ago. So yeah, and as you know, Brian, when you live through it, and when people summarize history and all, like, it gets simplified, or some of the
Totally.
things are not, it's kind of like, it feel like Chat GPT answers sometimes, right? It's like, yeah, kind of right, but not quite right, in the stuff, right? But anyway, so
No,
I try
I think you're
avoid
totally
seeing
right.
the recent history. Right? Yeah, yeah,
And it is so funny, because like when you've lived it, and then people are
yeah.
kind of turning to you as an authority, being like, okay, you lived it. And I'm like, well, actually, there are a couple of different narratives that are out there, and I'm not even sure. Like, I was there, and I'm not even sure which one is the right one. They've got, and there's so many. But that's why. By the way, Adam and I just embrace the fact that we're living fossils. By the way, we're not trying to fight it.
Yeah.
Um,
No, no, but what's common in all the themes of history, which I think we'll kind of get into, right, is this hardware software interplay, right, is the has always been, kind of the catalyst of change, right? Like,
yeah,
whoever got that right, or whoever were on the right side of that equation, right? By luck, or but or by planning, right? Ended up surviving. And no matter how great you were, like how wonderful, I mean, 3DFX was just like, just blew people away. And if you just look at how long the duration was, it was less than 24 months. Okay. It's like,
yeah,
back then, it's like 1 year of dominance, 2 years of dominance seemed like a long period, right? And things like,
right.
yeah, leadership changed very fast, right? And especially because, when the Moore's law was active, and the silicon cycles were faster, right? Like, 12 months to a chip, right? 12 to 18 months, we could do a completely new thing. Now it is 3 to 4 years minimum. Okay, minimum. If it's a brand new architecture, it's 4 to 5 years. We did brand new architectures every year, throwing away everything and redoing it, right, back then. So,
Because the process
the
changes are so radical, because this is like Denard scaling is alive and well during this
yeah,
era.
was
So
there, right? So, and if you just miss one cycle, you find yourself like, 2x off, right? Like it's just
right.
suddenly, right? You just misexecuted just one time. So the winners and the losers, those things shifted much more, much faster, which was exciting, right? In some ways, right?
You're
It's like,
right.
yeah. It wasn't like, oh yeah, well now, right now in the valley, it just shocks me that, I mean, that people can't even think of, like, that, who will beat NVIDIA, right? Oh, that's like, oh my God, don't say that out loud. Don't even say, what did you say? Beat
Right.
NVIDIA?
Totally.
Oh my God, it's just
Right.
in the stuff, right? In this, the evil Lord Sauron will come and, right, knock on your door, right? And in this stuff. So don't even say that. Even the big billion-dollar VCs don't want to talk about it, right? In the whole ecosystem. But that wasn't the valley, right? In the 90s, it was like everybody was disruptable.
Right. And so, you talked about the hardware software interface, because I actually honestly just don't know that much about, I mean, very much on the CPU side of that. So The GPUs of that era, I mean, are they? I know that they're getting like richer and richer in terms of their own computational power. And I at Sun at the time famously, did you ever deal with Leo at was your graphics card at Sun, Adam? This is a
No.
absolutely bonkers graphics card that had its own MMU, and they
Yeah.
had kind of they had kind of forked the operating system in a way that was not very good. But and then that thing had a lot of reliability problems. But what is the abstraction that folks are kind of coming to during that era? This is, I mean, because this is almost like, I mean, you've got kind of SGI and Sun, I guess, kind of the high end graphics end. You're kind of coming up to the game side, and I mean,
Right.
what are the abstractions of that era?
So everyone practically had their own proprietary abstraction, Brian, and then SGI proposed OpenGL, right? But it hasn't quite caught on, and it was kind of it got a bit of a branding that it was only for kind of non-real-time graphics or workstation stuff and all, right? Like kind of this high-end visualization stuff, but not for PC gaming, right? So and these APIs and there were some APIs that actually did CPU rendering, not GPU rendering, right? So 3DFX came up with their own API called Glide, right? So Glide was actually like like the Cuda of that generation in many ways. It's proprietary, but it was like tiny little API on which like the first I mean I still see the first 3DFX demos in my dreams, right? The Valley of Ra, and they would just blow people away, right? And then John Carmack did the GL Quake on it, on top of Glide wrapper. And so Glide was a proprietary API. And people were trying to bring OpenGL to PC, but the history was changed with Microsoft, right? Microsoft was the big kahuna back then, the dominant PC operating system.
Right.
So Microsoft formed this group to build DirectX, right? So Direct 3D was the first 3D API that tried to unify all of us, right? So they brought the 3D effects, rendition, S3, 3D Labs, NVIDIA, ATI, Zeng Labs, Diamond Multimedia. So there are 10 other names together, right? And said we're going to have one common API called DirectX. And it was kind of messy in the beginning because all our hardware were not all equal capabilities, right? So they introduced these things called caps bits. Okay, so you declare your capabilities, what your GPU is capable of in these caps bits. And it was a caps bit nightmare for game developers, right? Which caps, it wasn't very, if I go back and look at all the, code we made people write and all, it was messy, messy, messy. And, but Microsoft was like, key dominant factor, right? And it was API standard that will be available on Windows. And 3DFX was, brimming in success with their proprietary API. So they dragged their feet to get onto DirectX. And Microsoft iterated DirectX every year, actually twice a year, sometimes. And by the time they got to the fifth version, it was pretty good. And what we were doing as hardware guys, we were actually building the hardware for the API. Actually, if you just pass on that statement, that is one of the big differences between a CPU and a GPU guy, right? I tell people like the GPU people think in terms of APIs, CPU people think in terms of ISA, right? What's my instruction set architecture, right? Yeah. And the GPU guys think in terms of what is the API, and that API contract became the DirectX, and NVIDIA and S3 and ATI were the first to build native API compatible accelerators, right? And that was actually the reason why 3DFX lost, right? Because they weren't very compatible with the Microsoft DirectX.
DirectX,
and yeah, and NVIDIA and ATI eventually kind of, S3, wandered off into, just like, when shiny objects happen, when hype cycles happen, people go after hype cycles.
Yeah,
S3 went after the hype cycle called web without kind of, being core focused on, what what they were doing. Whereas,
interesting.
NVIDIA and ATI stayed focused on doing graphics, and so kind of, S3 fell by the wayside. Um, so
Companies that
yeah,
are contemplating a pivot to AI treat this as a
yeah,
cautionary
exactly,
tale.
yeah, yeah,
Like,
yeah, yeah. Hype, hype,
it-
hype. Yeah, hype versus basics, right? That's kind of one lesson learned.
yeah, interesting. So S3 decides it's a web company. It wanders off and
Yeah,
flies into the side of the
yeah.
mountain.
Because I
Um,
remember the interim CEO we got said, see, at that time, just I think Nvidia got the Xbox design, and they went IPO and their stock popped, and it was pretty good. But relative to all the internet companies, their PE
right.
ratios and the stock was low, right? So he gave this famous talk. He said, "Hey, if you guys wildly succeed, the best you'll be is at Nvidia, which was like some $20 stock or something, right?" And and we were at
Oh
like three
wow.
or four. And then he said, "But if you go to this internet stuff, right? Look at our neighbor. We had this company called Exodus. Actually, you guys coming from the server and storage world might remember this company called Exodus. That was the first kind of AWS-ish
Yes.
thing.
Yep.
Yeah, yeah, and they were our neighbors, and they were like $120 stock. Okay, and they, of course, they crashed and burned in a couple of years after. So our CEO says, if we look at Exodus, we should be Exodus, not Nvidia.
Yeah, and this
And,
is Exodus
uh,
Communications, I believe, right? This is
yeah, yeah,
and yeah, I actually had a bunch of Exodus people that I worked with after Exodus,
yeah,
and do not recommend.
yeah, yeah, yep.
Um, that is well, and that is amazing, isn't it, Rasha? That you think like the best you're going to do is Nvidia. By the way, if you could be like, hey, I just traveled back from the year 2024. I've got a super funny story for you about Nvidia. Um,
Yeah, yeah,
so and it just God, that is so telling, and we're trying to catch, and obviously like an S3 is not going to be. I mean, you're a graphics hardware company in your DNA. You're not going to become a web, like it's meaningless for you to pivot to. You're not going to be
meaningless. Yeah, he
anything.
sold. They sold the graphics IP to a company called VIA. You remember VIA used to make
Right,
chipsets. They were the most, Taiwanese company VIA, and
right, yeah.
yeah, and said the rest of it will, build, interesting, web devices and all that stuff. And yeah, anyway, we
So
can write chapters and chapters on that. So
right. So at some point in here, you're like, I think I'm leaving this company, and you went to
yeah,
ATI happened shortly
yes,
thereafter. Yeah. So
yeah.
ATI, which I mean, it should be said, the two survivors of that era are ATI at AMD and Nvidia, really, right? I mean, are there
Yeah.
any other survivors from
No, no,
that era?
AMD. Actually, it was just really ATI and NVIDIA because AMD didn't have graphics, right? AMD did
Right.
not.
Yeah. Right. Right.
AMD
Right.
was just a CPU. And Intel had a graphics team, right? So, I gave this talk at Stanford in January, and also in, recent. I was in China, and I gave the similar talk at, Shanghai Jiaotech, what's considered the MIT of China. I said, every 5 years or so, Brian, in the graphics world, we declared, like, there was a big board meeting saying, this is it. This is the end of discrete GPU. We should go do something else. So, one of those very early on is when Intel said it is going to integrate graphics into the chipset.
Right.
Okay. And oh my God, in the PC by default, like, you have to buy Intel chipset and Intel CPU. So why would anybody buy a discrete GPU on top, right? It's dead, right? So they declared death of discrete GPU in like 97, 98, and everybody was looking for kind of alternatives, right? And Nvidia
Yeah.
also got into chipset business. If you remember, like they did the Enforce, and it's like they did the best AMD chipset for a while was from Nvidia.
Right. And
So
so this is actually an interesting, because this is going to be a theme that we're going to see as we kind of advance in time, where you have a general purpose CPU, general purpose thing, say,
yeah,
hey, I can actually, that special purpose functionality, I can actually deliver that as part of this general purpose vehicle. And
exactly. Yeah,
it,
yeah, yeah,
I mean, this is what I think what you called generality in
yeah, yeah,
and kind of that the power of that generality. And I mean, I remember, I mean, I during that era, my observation myself was that general purpose compute trumps special purpose compute every time, which of course isn't exactly, it's not true right now anyway, because general purpose I feel that that's true in the limit, and it's certainly
yeah. No,
true.
what's interesting, Brian, right? And it's always kind of easier connecting the dots when you look backwards, right? It's hard to connect dots forward, but you can connect the
Yeah,
dots
right. Yeah,
backwards. So the way I would frame as is, see, when your problem space, right? Can scale more and more with computation. Okay. For example, graphics was one such thing because, we kept getting increase in the number of pixels on the screen, right?
right.
When I started my graphics career, games were shipping at 320 by 240. Okay. I saw the transition to 512 by 384 to 640 by 480 to 800 by 600, 1024 by 768, right? 1280 by 960, and when we were doing the first 1920 by 1080, it felt like we were in, immersive reality, right? That's
Right.
1080p.
Yeah.
Now we are at 4K, right? So the pixels kept growing up, and then the amount of computation on each pixel also kept like exponentially growing up, right? So the scale, like if I can throw a bigger GPU at a game, you got better quality, better performance, better stuff, right? So that's a scalable problem. Whereas take an example of an image encoder or a decoder, like video encoder decoder. Okay. See, after I hit 30 frames per second or 60 frames per second on 1080p or 4K, you giving me a bigger, larger encoder and decoder doesn't make any difference for me,
Right.
right? It's completely waste, right? It's that's a contained problem, right? Once you hit a particular quality level, right, and a time interval level, you don't need more. So I think we have to divide problems into those categories, right? So graphics and now parallel computation and now this AI computation, right? Larger and larger, neural nets, right? And more parameters, right? Seems to not end. If that starts tapering off, like say somebody says you're not going to get any more fidelity beyond 1 trillion parameters, let's just say,
Right.
right? I'm just
Yeah.
throwing a number right in the stuff. Like it's just diminishing returns after that. It's a plateau after that. There is nothing more. Then you could say that, oh yeah, okay, right? Something that is fixed, right? Non-scalable, right? Fixed is the right answer, right? And we could get 10x efficiency on building something that is fixed,
Well, I
right?
was
But
just going
when
to
the
say that.
problem, yeah, yeah.
Yeah, well, that when you, because I think it's a really interesting way to think about it. And I was thinking about like in like the decoders as like encoders, decoders is an example of that, where once you do hit that point where it's like, no, there's no point in getting better absolute performance, then you do get to drive to efficiency. Then these other kind of things like power and economics.
Yeah, exactly. Yeah, you can drive those and smaller. Now we have like amazing 4K and 8K, encoders and decoders sitting on your, phone,
On
right?
the phone, it's crazy.
Yeah,
Still
right. It's crazy,
crazy
right? So
to me.
yeah,
At such low power, I mean, like, I
yeah,
mean, every time I kind of complain to myself about like the battery life of my, a part of me just wants to like just punch myself in the mouth, being like, how are you possibly like, I want to conjure my past self who can come up to me and be like, are you,
yeah,
what? You're complaining
yeah,
because
yeah,
you're like, your batteries died in the grocery store while you're having
yeah,
a real time video chat? Are
yeah,
you like,
yeah,
Right.
yeah,
I'm so
Your
sorry. Like the
your
future sounds
4K
really
phone,
terrible.
right?
Yeah.
yeah,
Your multi-gigahertz processor with a
yeah.
gigabyte of memory. Really? I'm sorry.
Yeah.
Brian, the first time I saw a real-time stream, a DVD quality video stream of a live event, okay, I literally cried, right? There was tears through my eyes saying that, oh my God. I mean, it's like, because I was involved on the video pipeline too, right? Like at the start, how difficult it was to just play video locally, right? Like, the
Right.
first, when we got DVD playing on a PC, right, without dropping a frame, okay, was like, we were like, you know, celebrated like, oh my God, it was just a major achievement. And now you're doing that across internet, right? Both like, a camera capturing, encoding, streaming and decoding and at DVD quality, right? I mean, DVD was the big thing back then, right? We didn't even hit 1080p back then, right?
Well,
I was
and
just,
like,
yeah,
and really, like, I mean, yeah, but I mean, that's the kind of stuff that really like has meaningfully changed people's lives. I mean, I know it's like, yes, the internet is awful in plenty of ways, but it is worth a moment of being like, that is so amazing. And you think about how amazing it is that a grandparent that lives thousands of miles away can have can watch a recital that their
yeah,
grandchild is in,
yeah,
and like, holy smokes. And it's a lot of technology at every, you got the at the edge in the internet, and then of course I mean, kind of both ends of this. And as you say, it's like there's a lot of
yeah.
silicon that
And
has
and then
that.
getting audio right on that. As we were
Right.
talking at the
Right.
beginning, right? That's people tend to say, oh yeah, audio. It's like where whatever low bit rate and this and that and all, but getting audio right, is another challenge too. But yeah, it's amazing that they all come together, and but it's an example of, right, kind of contained, non-scalable problem,
Right.
right, in the sense that just throwing blind more compute at it isn't going to make it any better, right? It is other things that you have to do to deliver audio and video well on the internet, right? I mean, compute is important, but like this fixed function algorithms, right? For, once we got standards, H.264, 265, AB1, MPEG, once you have a standard, I can then do a very efficient, hardware implementation of that standard, right?
Right.
If there is,
Right.
and that's one of the things I ask, like, the AI hardware companies and all, it's like, hey, I'm doing this great AI chip. Okay, say, so what's your programming model or what's the API? We don't have one, but we are, flexible. We are programmable,
Right.
and we can attach to whatever, right? And the stuff. And I say, oh my God, okay, that's the problem, right? You don't
Right.
actually have an interface to your architecture. And this was the point I made at the the Hacker House talk on Saturday, right? I said, just kind of switching gears a bit, Brian. I read this statement. I think it was in 2004 or five in a small handbook called Data Parallel Programming Handbook, and it was a collection of papers by eminent people from HPC. And there was a statement that said, in the history of parallel computation, there is no architecture that was successful whose programming model was different than its execution model. Okay, again,
Interesting.
repeating, whose programming model and execution model. Okay, so execution model is how the hardware executes a stream of instructions, how it fetches data, its cache hierarchies, all of those details. Programming model is how a programmer expresses a sequence of computation you want the hardware to perform, right? So, and I didn't understand that statement, right? It felt, you know, it felt strange. It felt like very interesting, but I kind of couldn't quite like, put my finger onto it. And and again, coming from the graphics world and all, I wasn't that an expert on the history of HPC, Cray supercomputers, and like all of those stuff that happened in that world, right? We were coming from the PC side of things, so I didn't live the parallel computing world. But the reason I say that is, the reason now kind of, why CUDA is so successful, okay, is the CUDA programming model and the NVIDIA hardware execution model, how their SMs execute. It is one-to-one mapping.
Right.
You can read the CUDA code and you can kind of, say, oh, yeah, this is what is going to happen inside that SM, right? So when people try to kind of, implement CUDA-like languages on a different execution model, they made it work. See, making it work is one thing. Making it work fast is a completely different thing,
Is a
right?
completely different thing. Okay, so
Yeah.
that's a super interesting statement, and I just to pull at that a little bit, because I kind of think that the general purpose CPU running systems workloads, or even x86, may be a counterexample to that, because the programming model and the execution model don't exactly match. And just to play this out a little bit, because we had, when Denard scaling ended,
Mhm.
we had this memory wall that that felt impenetrable, that we worked around. I mean, on the one hand, you worked around that multiple cores for certain, so that's a degree in which the programming model and the execution model do line up. But speculative execution is an example where the programming model and the execution model don't exactly line up, and it has been
Yeah.
a source of real problems for us.
Yeah, exactly. So, we can talk about the programming models, right, and the execution model. I mean, I'd call the most successful programming model in the history of computing, right, is, single-threaded C programming, right?
Right.
We built the
Yeah.
entire stack with C, right? I still think that, kind of C is, to me, the language of computer gods, right? And when I say, Raja, what language are you most comfortable with, right? That English or my mother tongue Telugu or in the stuff, and I say, often half jokingly, I say C. Right? I think in C. I may sometimes talk in C and all that stuff. But if I look at C code, the reason I like C code is that I can write every statement, right? What it turns into, right?
Yes. Yeah.
Into instruction stream, you can kind of clearly see, right? Like, I'm not talking about
Yes.
libraries and other stuff. The core, C, right? Like, declaring a variable, operations on the variable, right? And if then else classes and all that stuff. You can see, the load compute store
You can
paradigm of the
feel
C.
the assembly underneath
Yeah,
you.
you
You
can
know
feel
what
the
the assembly
assembly
looks like.
underneath.
Yeah.
It's like in the stuff,
Yeah.
right? And then compilers came and made the efficient, getting efficiency out of a processor job a little easier than me writing assembly, right? And then
Right.
the out of order execution was this. Oh, you know again, out of order, if I could be executing single threaded code really fast, right, frequency was at 1000 gigahertz by now or something like that, we wouldn't actually do speculative execution, right? It
Right.
wasn't, right? So we could do more parallel computing slots even on a CPU, and to exploit to run more than one instruction at a time, right? We invented, this out of order thing, right? We tried VLIW, and
I
then,
was
like,
gonna say, yeah. Yeah.
which we said, let compiler figure out what can be executed in parallel, and that never worked out, right? And then out of order came, and rest kind of was a bit of history. But one example, actually, just stepping back to kind of the original thing, Bryan. I don't know if told this analogy the last time we met, but I've dealt with the CPU versus GPU versus FPGA versus, like, kind of ASIC question, for last 15 years, right? Like, it comes up. And if you ever work at a company where you have all of these as options, man, it is kind of like you're fighting religious wars between these entities, which I, unfortunately happened to work at one such company where you had all these processing units. In fact, I jokingly say the reason why NVIDIA won is because they had only one thing, right? They didn't have all this, options, right? If they even had a CPU, they would be screwed, right? They would be fighting, like, so many, this stuff. So the
That's an
analogy I
interesting
use,
point, actually.
yeah,
That's a very interesting point, because,
yeah,
and just for give other people context, so you were the chief architect at Intel, where
yeah,
you I mean, this is true of AMD too, where you've got at both AMD and Intel, although I think at you've got all these different things under the same
yeah,
roof, and
yeah.
it's diffracting, and and it also does not result in like the best things. You think you'd be like,
No, no. So I'll
I mean,
tell you,
it's
and
surprising.
I'll give you an analogy, which I think, that you and, all the audience will very much connect to. Okay. So think of, if I would switch computation to transportation. Okay. Let's use transportation. analogy. Okay, so I live here in South Bay in San Jose, right? And I want to go to San Francisco, right? I have a bunch of different transportation options, right? Or I want to transfer a package, an Amazon package from point A to point B. There are a bunch of different options. One is a car, right? I can go sit in a car and drive, right? And or I can go drive up to the train station nearby me, Caltrain, and get on a Caltrain station and go. Or
Roger,
I
I'm
can
going to
take,
apologize. Adam and I have had so much of our lives spent together on Caltrain that any mention of Caltrain is very evocative.
That's right. And go and maybe you can go on Caltrain and maybe
right,
eventually you'll get
yeah,
there.
yeah,
Right.
yeah. So then you also have buses, right? So think of CPUs as cars. Okay. So from point A to point B, I can get to my destination in a car. Okay. Yeah, I can carry 4 people. Maybe if I have a minivan, I carry 6 people, right? But if I have 1,000 people that need to go from point A to point B, okay, a train is far more efficient, right? You'd agree, right? If I have 1,000 people. So, and in between is a bus, right? A bus is kind of an in-between stuff, right? And a train is kind of far more efficient. So CPUs, when you have small payload, CPUs are really efficient, right? You don't actually even want to think about a GPU, okay? And it takes you to the end destination. So today, and GPUs, the early generation GPUs, all the way in the first generation of CUDA GPUs, before we introduced tensor cores, are kind of more like these big buses, right? And when we introduced tensor cores, I call it, they became more like train stations, right? In the stuff. But you still need to get to the train station, right?
Yeah,
You need to get in your car to the train station. So you can't build a computer without a CPU, right? No matter what anybody says, right? A car is still needed. Even after I get down from the train station on the other end, right? I need a car to get to my home in San Francisco, right? So again, the transportation analogy works very well. And in this scheme of things, you might ask, okay, Raja, I understand, cars, buses, and trains. Okay, so CPUs, vector GPUs, and now tensor kind of GPUs. Now, where do FPGAs fit in
Okay,
this?
can I guess? Because I've been thinking, this is what I've obviously been thinking. As I the analogy, I'm like, where do FPGAs fit? I'm like, FPGA is by foot. FPGA goes absolutely anywhere. I want to go in the High Sierra. I can go wherever I want with an FPGA.
Yeah. Uh-huh.
But it's not. I mean, I think part of FPGAs are not necessarily fast. I mean, they are fast. Like, if you want to go, they're not going to be Mount Whitney.
Yeah, they're not going to be fast on the roads and the train tracks, right? But they may be faster than car and a train on a pile of sand, right?
Or to the top of Mount Whitney. You're not taking a car to the top of Mount Whitney. You can
off terrain.
Driving to the top of Mount Whitney. I will beat you there on foot.
Yeah. I mean, FPGAs have two personalities. One is, I call them, all this construction vehicles that you see, right? They also have, they look like, transportation vehicles, but they're only used for building the roads, right? Building construction, building stuff, right? They're very useful. They're very, very important. Yeah, you can use them to drive on the road. Okay. Yeah. In fact, they go on the road from one transportation site to another transportation site, but you don't want to commute on them, right? You don't want to use them for your daily use, right? So FPGAs.
So your analogy, the FPGAs, you got construction vehicles are your like dozers and so on, or FPGA, which actually makes more sense. Yeah. Okay.
Right. Yeah. Okay. Yeah. There is another interesting aspect of FPGA as well, Bryan. Right? Is that analogy works for many things, but FPGA also has another interesting property, right? I kind of call it, just imagine, the Lego car, the super cool Lego car you can build. Okay. Right. Like, with its own custom stuff, and like it's a good prototyping mechanism for a new bus or a new car and all that stuff, where like, all this kind of, robotic car parts that I buy and kind of build my own car, right? From the parts as a prototyping vehicle. All these parts are very customizable, so I can build a car and test it out. Like, everything, does it work? Is it in the stuff? It won't hit the, my finished car cost or performance or energy efficiency. but I can prove out a lot of things, right? And especially if I only need to build a dozen of them, right, to try it out. FPGA is the best way to do that. Right? You don't want to tape out a chip and design and this and that and all that stuff, right? So there are also good Lego kits, right,
Yeah.
for CPUs, GPUs, and any ASICs. So that's kind of the way I see it. CPUs, and all of these are transportation mechanisms, and they run on different infrastructure, right? And when people ask me, like, hey, why can't you just add, like, why couldn't a GPU win on AI? Sorry, a CPU win on AI, right? Like, why couldn't you just deliver more bandwidth and all that stuff? I said you could. There is nothing architecturally kind of, special about all of this stuff. But remember that the infrastructure, the roads, right? The road sets your speed limit, right? How fast you could go, the road infrastructure, right? Versus a train infrastructure, right? So your infrastructure is kind of like your memory subsystem, your bandwidth, all those things also need to be high performance, right? For you to deliver a GPU like throughput. So you can't just, get GPU like throughput or a train like throughput on a road,
Right.
right?
When I think
Yeah.
and this emphasis on memory, I think, is really important because I think and it also is a difference between. I mean, some of these workloads, as you start to, I mean, like these LLM workloads are really quite memory intensive, right? I mean,
Yeah.
they really balance memory and compute in a way that you don't see in these graphics oriented workloads, for example.
Yep. 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 No, I need, like, literally, right? If you take 1,000 people example, right? If 4 people can fit in a car, right? You need 250 cars, right? Going, right? Uh, you know, going, and you can fit them in one train, right?
Right.
1,000 people, right? So that's basically what's happening with these LLMs and this big AI workloads is the number of packages, right? That you need to move across is so much that you can just use cars, right? Right. Now to do a small prototype, quick and dirty prototype, right, with small number of parameters, CPU is awesome, right? Like you can see Andre Karpathy's llama.c thing that he does, right? In fact, his single-threaded C code runs on a CPU. And it's actually most beautiful thing to understand the whole algorithm and all, right? Because we are, much more comfortable with getting in a car and going from point A to point B, right? We live
Yeah.
in California, right? We understand we can't live without a car. Now, just continuing on this analogy further, why, okay, now there is NVIDIA GPUs, and they are AMD GPUs, Intel GPUs, right? And then, some other AI hardware that try to mimic kind of NVIDIA-like stuff. Why haven't they been successful? Why is Cuda? What is the difference between, if they're all trains and buses, right? How come, nobody could compete with NVIDIA? So for that, I switched the analogy. Instead of moving people, let's just say we are shipping packages, right? Like Amazon packages. Okay. So now the package, the shape of your package, right? Let's say your trains are all rectangular compartments of a given size, right? Each compartment is a given volume and it's rectangular. And let's say all my packages are rectangular. Okay, I can pack my train compartment with 100% occupancy, right, with no air gaps, right? And uh, in one shot, I can transport a number of those packages. But let's say my packages are weird shapes or some cylindrical shapes or some other kind of shapes. And when I load the same train up, I have air gaps, right? I'm not utilizing it fully, right? The more concrete example, right? The compartment size on AMD, for example, AMD architecture, it's a 64 wide, packet size, and NVIDIA is 32 wide. So when you have packages that come from CUDA, even if that was translated through HIP and ROCm, they go at half utilization on AMD, unless you go repack the code,
Yeah. Interesting.
right? Right. So while you can make it work, your utilization, unless you ask the developer to repack, okay, is inefficient, right? And that's the challenge with the popularity of Cuda. Like, it's slowly, I call it the Cuda virus, right? Like, it's spread all across. Developers don't even write Cuda code. A lot of people, they're writing PyTorch code or something, but the implicit packing of, your data in compute that comes through various libraries and framework is biased towards the NVIDIA sizes, right? And that's why it is not straightforward to just attain performance. And performance matters, right? And it's not just compatibility, right? Because if I'm parallelizing a workload, if I'm putting all the effort to get to a GPU, I'm doing it for performance. I'm not doing it for for compatibility, because if I just cared about compatibility, I would never even write anything in parallel, right? I would just write a nice serial code and be happy with it. And so when I put that effort, and if I don't get performance, I'm disappointed. So that's the reason for Cuda's stickiness and popularity. Beyond being the best architected hardware software co-abstraction. It also taught people packing things in a particular way.
Well, and just as you said, the execution model matches the programming model.
Yeah.
So if your if your execution model has a mismatch with that programming model, and it does remind me of like the non x86 x86 parts that existed for a while, and ultimately like didn't deliver
like
on
the transmeta stuff.
I was thinking you got you get the transmetas for sure, and then you have those folks that were also doing binary translation, and and that all kind of withered because you're undermining the economics of it, or you're undermining the performance of it, and you really you really have to be desperate to run on the it's like actually I really want to run on Spark or MIPS or Power, and it doesn't feel like it's not a kind of a long-term kind of a thing.
So that's what Bryan led me to this, like that equation, right? That hey, it has always been about, whether it's CPUs, GPUs, whatever, right? It was about this blend of performance and generality, right? So that's why the architectures that won, that kept that performance times generality equation, they led, right? So people said x86 was going to die many times, right? Even through kind of 80s, 90s, and all that stuff. But thanks to they had the generality covered with the Microsoft partnership, right? The most popular operating system, and then of course, Linus did Linux on x86. But because the Dennard scaling and Moore's law was active, they kept the with the compatibility, they kept the performance going up 2x every 18 months or so, right?
The presence of AMD really, because Intel did fumble to Opteron in 2004, 2005, 2006 kind of time frame through there, and where Intel got very distracted with IA64 and VOIW and the kind of magical compilers, as you alluded to earlier, that didn't go anywhere.
Yep.
And it was really AMD that refocused them on x86 and Yamhill, right? And realizing that Intel developing Yamhill, which was effectively the implementation of the AMD.
No, but by the way, that's a very interesting point in history, right? So because of the end of Dennard scaling, right, we couldn't just increase the performance, right, without impacting the generality, in the sense that, see, we tried keeping generality the same, in the sense that, hey, make a single threaded program go faster and faster and faster and faster, which the main tool we had was frequency. Okay. Right. So frequency scaling ended, right, in that, early 2000s, right? So we've been flat on frequency since that time frame, right? Really, like, we hit that 3 gigahertz point. Yeah, down even, right? And so Intel said, oh, yeah, so how do I get more performance? So let me go and pack generality by, like, VLIW architecture. and make the compiler, but still hide it from the developer, right? So don't let developers change anything, okay? My magic compiler will exploit the parallelism, right?
My magic
Will never
compiler that,
break.
by the way, I can't tell you about and I don't yet have. My magic
Right, right,
forthcoming compiler.
right. And then AMD and kind of with Microsoft stuff said, well, it is time for us to impact the developer needs to contribute here, right? The software guy needs to come into the play. So when multi-core was introduced, right, the multi-core, right, that's how
Yes.
AMD went ahead. Multi-core was needed software changes, right? It didn't, magically, help old code. It only helped new code,
Well, okay, so
right?
actually on that though, I actually think to your point of the programming model matching the execution model.
Yeah,
So that I actually don't think that that's quite right, because what had also happened is the rise of SMP in the late 90s. And part of the reason that actually Sun flourished when lots of other companies perished is because Sun made a very big bet on SMP.
yes,
And
yeah,
and there was an idea at that time that like you cannot make SMP scale. You can't make the operating system scale. You can't make the databases scale. Like you can't scale this out to. And I remember I forgot. I actually, I'm sorry. I'm just going to name and shame him. Larry McVoy sent me a mail in 1995,
mhm.
saying in the confident Larry McVoy way that operating systems will never scale beyond 8 CPUs, and
Yeah,
that's
yeah,
and that wasn't correct, and that
yeah,
wasn't
yeah,
correct in part. I mean, it and this was one of these, talk about like hardware software co-design, where the hardware did get a little further ahead of the software, and where we had hardware systems that
yeah.
should have scaled better
I
and
think the
didn't.
blind spot, Brian, then was I think we didn't, I'm not on the CPU side. I'm just kind of saying the industry statement that the user level parallel, like, it's basically all the benchmarks, right? That we, like I made this statement on Twitter saying that, you become what you're measured by, right?
Yeah,
So we were measuring by single user benchmarks, right?
that's right.
So
That's
like,
right.
how can I scale a single user experience? And, from that standpoint, that is still true that there is not much like, in the stuff, but, the whole transactions that the web and internet and like, that we'll have, literally billions of users, right? So the user level parallelism meant that I am presenting multiple computers on a single computer, right,
That's
to
right.
each user, right? That I think our imagination, collective imagination, didn't take that into account, right? So we underestimated the user scale, right?
I
And
think so, and I think this is one of those where there was an impedance mismatch a little bit in the industry, because you did
yeah,
have people who were like, "No, you don't understand." Like there are many workloads that don't parallelize. And I remember being at the time, 'cause I'm at Sun starting in
yeah,
1996, and I'm being
yeah,
like, "No, you don't understand. The thing that actually needs to scale is the actual operating system kernel. If the
yeah,
operating system kernel scales, you can actually run a bunch of single-threaded processes. If you
yes,
provided
yes,
that you actually
yeah,
need to do a lot of work. And in particular, I think a lot of people didn't realize that like Oracle, the dominant database, commercial database at the time, this is true for
yeah,
Sybase and
yeah, yeah,
Informatics
yeah,
as well. These were actual like these were single process databases that had multiple processes that shared a global area, and so they
yeah,
actually had multiple processes sharing memory rather than and so
yeah.
not
I
everything in
mean,
those databases.
now that you say that, I think about, and then, we said, okay, operating systems, you don't scale, we don't care. We'll put you,
Yeah.
underneath with a virtual machine and have multiple operating systems running on the same machine, right?
And I think what we also just learned is that, and I think Bonwick's kind of observation, Jeff Bonwick's observation that early on was that if we have a machine that has n CPUs, and we can get it to be non-pathological at n, it will perform well at n over 2. And
Right.
so, I mean, the presence of the E10K 64 processor machine, it's like by the time the late 90s rolls around, like the operating system runs really, really well on certainly on 8 CPUs and on 16 and on
Yeah.
32. And Adam, like the Serengeti systems that we had with 32 CPUs, it's like,
Mhm.
and so then it's like you've got this kind of big question about how do we circumvent the memory wall? How do we scale the memory wall? And there's the
Yes.
VOIW idea coming out of IE64, And then I think, and Russia, I'd be curious to know your perspective on this, but I think it's the Piranha folks at Deck Whirl that are the first one where they are I think the first ones to take multiple alpha cores and put them on the same die. And I remember thinking like, hot damn, that is a really good idea. Putting multiple cores on the same die is a really good use. And this is before the end of Generality scaling too. This is in like the late 90s, early 2000s. I'm like, that feels like that's a direction that makes a lot more sense. And because to your earlier, I mean, I'm still ruminating on the programming model matches the execution model, and multiple cores on the die. The programming model matches the execution model. The idea of having, like I've already got this, like, oh, I've got this big, 64 CPU E10000 server, and I'm actually just like putting that thing onto a die. Like there's no the level of magic was it was certainly much less magic and magical thinking than VLIW. And Raja, I've actually got a very funny story for you about VLIW. And so I went to a talk at Stanford given by John Crawford in what would have been the Merced hype peak. So I don't know when that would be, like maybe 99. I don't think you were with me. I think this would have been
that peak was definitely late 90s before I was at Sun.
Before you were Sun. Okay, so I think that this is like 99. This is when, because was Roger working on the Merced port when you arrived, or that already?
No, we didn't talk about it by the time I arrived.
We didn't talk about it. Okay, yes. Yeah. Okay, yeah. So this must have been like 99. So because we did, Roger, I don't know if you remember like Project Monterey. This is the collaboration to do Unix on Merced. Merced being the first instantiation of IA64. And so John Crawford is giving this talk at Stanford, and I'm like, it's kind of like open, free to people to attend. I'm like, oh, this is great. So I went in this packed room in Stanford, and at the time, I'm like, I don't know, VLIW seems interesting. Maybe this is interesting, and we were working on a port, and he's kind of explaining, doing the classic like 8 queens problem, which is like, okay, great, wow. If I want to solve 8 queens, this thing seems really
it's gonna rip.
awesome.
Yeah,
it's just amazing. Unfortunately, I don't know how frequently I need to solve the 8 queens problem, but boy, when I do, you're my first call for sure. And he's showing all of the spec benchmarks, just to your point of like, you are what you measure. And IA64 is doing really well on all of them except for one, which was the GCC benchmark, and it's doing terribly on the GCC benchmark. And I'm thinking like, I'm just kind of a sprout over here. I'm kind of a young Turk. I don't know, but doesn't that feel odd that the GCC, and there's this voice at the back of the room who's like, hey, can I stop you on that slide? The GCC, the only one of those things that's actually a real world benchmark is the GCC benchmark. That's the only thing that represents reality.
Yeah.
And you are doing terribly on that benchmark. And I was like, oh my God, this guy. And Crawford is kind of like stammering a little bit, and everyone is kind of turning around like, who is this voice at the back? And it's John Hennessy.
Yeah.
And
nice.
and I'm like, I think I have just witnessed a Silicon Valley gangland slaying. I mean, this is like, John Hennessy tearing off in a car, later to be the president of Stanford, right? I think, was Hennessy, am I making that up?
Yeah. What's fascinating is it took 20 years from that day for Intel to fix GCC or their GCC performance, right? And it took 20 years.
20, it's amazing. Well, because and actually the line that stuck with me is, and this was asked as a question, doesn't this willfully ignore all research on this topic? It's just like, but yeah, in GCC 20, because like it's a super sloppy workload. GCC is just like, it's just pointer chasing, and it's like it's the kind of thing that VLIW is going to do, and VLIW also does very bad at, because not only
I mean, they had two issues, right? Like, there is a technical issue and there is a political issue with GCC. Okay, Intel struggled with for years, which is, hey, if I contribute optimizations to GCC, right? Like, all the stuff, all my secret sauce will be out to everybody, right? So, this whole open source, closed source, right? Battle went on for a long, long time inside Intel, right? On the compiler optimizations and they're contributing. So they hoped GCC would die and everybody would use ICC and, right, that that would be the compiler of choice. But then ICC became just a benchmark compiler, right? It was, it ran benchmarks and little of anything else that anybody trusted it to, work,
which is kind
right?
of
So
tragic because it was a
yeah,
good compiler. I think anytime
yeah,
I could
yeah,
get the time of day at anyone from Intel, I'd be like, you guys should really open ICC, and they're like, no, never gonna happen. I'm like, all right, moving right on.
yeah,
So,
yeah, yeah,
okay, but but this is really, I mean, I love your casting of history in terms of programming model versus execution model, where these things kind of came into tension, and where folks were where there's a divide that people were willfully ignoring. So,
yeah.
in terms of where does that put us today in terms, actually, no, before I get that, I got one other question for you, because I think the other thing that is like really interesting to me is this: you kind of have these things that become economically, there's so much demand, broad demand, that they kind of economically they become ubiquitous. And
Hmm.
then something else comes along. It's like, hey, as long as those are economically ubiquitous, I've got another thing I want to do on those, right? And this is like, Adam, this is obviously Flash, and from a storage
Hmm.
perspective,
Hmm.
what we did with Flash at Fishworks. But then it's clearly with the GPUs now, with researchers realizing like, hey, wait a minute, we've got these like these vastly parallel matrix multipliers out there that have been designed to like handle polygons and triangles very quickly. I actually like think I could use that to train a neural net. And I mean, that's like in the 2012 time frame, right, Raj? I mean, and
Right.
that is
Yeah.
a huge breakthrough, but it's a parallel that we've seen throughout in history, where someone's like, actually, I've got another use for that hardware that may give this thing second life from
Hmm.
a you think that you've made, who cares about the the number of frames per second, except for outside a couple of gamers, once you've exceeded human cognition or capability. But no, wait a minute,
Hmm.
actually now we're going to use this thing to train neural nets, and now it takes off again. um I mean, first of all, is that an approximation of history? How
Yeah.
how
Yeah.
how
Yeah. Yep. Yep.
read us through that.
So the early so what happened was basically, right. So the gaming 3D graphics survived, right, and in 2002, okay, um, we moved to introducing floating point arithmetic. Okay. And we did the first floating point we did was an FP24 format.
The first
Uh,
floating point in a GPU was only in 2002.
is 2002, right? So,
It
and
was all integer before that.
what's that? It
Was
was
it
all,
all
yeah, it was all integer or fixed point.
Fixed point. Yeah.
Yeah, fixed
fixed
point stuff, right?
point?
Yeah, yeah.
Oh,
Right. So
right.
first floating point was actually done by ATI, shipped the first one, FP24, and Microsoft did DirectX 9 with the programmable shaders, right? And then 2005, we did FP32, IEEE FP32 format, right? And so every, these things called game consoles, right? The Sony and Microsoft, Xbox,
Yes.
PlayStation, Nintendo
My,
stuff.
my
So what
teenagers make me
happened?
aware of these things. Yes.
So this, whenever a new work generation of game console launches, right, it gets a lot of hype and a lot of excitement. The PC GPU sales drop. Okay, so right, so there's a period, a game console launch year, and the next year, you get a dip, right, in the PC GPUs. And in circa 2005 timeframe, we were kind of experiencing that dip after Xbox 360 and PS3 launches, right? And both us and NVIDIA, ATI and NVIDIA, we were like, hey, we need to. And then the integrated graphics is also occupying a whole bunch of market. Mobile laptops have become, very popular, right? They have very high volumes. So this big honking discrete GPUs that go into your PC, desktop PCs, right, were experiencing a downturn,
Interesting.
right? So uh, we were looking for, hey, what else can we do beyond gaming on these GPUs, right? Like, so it was a, kind of a solution
Okay.
looking for a problem in
Looking for a problem.
2005 time. Yeah.
Interesting.
And then we saw, the Stanford guys, right? Mike Houston and Ian Buck and Pat Hanrahan's guys, were the first ones that were, hey, we can do matrix multiplies, we could do some fluid simulations on GPUs, and they coined the term GPGPU, general purpose GPU, and they even did the first, general purpose GPU language called Brook, and they were, GPGPU became a paper minting machinery, right? Like, basically take any classic algorithm that was there out in the world for the last 10 decades, and port it to GPU, and you can get your paper published. So academia got all on this, like, take some parallel algorithm, map it to GPGPU, and get paper published, right? So
Okay,
that was
this
was
is
like,
happening. This is like it sounds like 2005, 2006, 2007. Is that
yeah.
okay?
That time frame, right? It started
Yeah.
in 4, 5, 6, right? That time frame. And but one thing was clear, right? The GPU languages, right? They look like C, right? All of, actually, even micro shading languages and all, they all, when you look at the syntax, you'll be very familiar. It looks like C with some weird constraints, right? Weird constraints and weird extensions. It's very readable if you're a C programmer, but it wasn't C. The biggest gap for something being a C, right? So GPU
That's
didn't
great.
support pointers. Okay, so Cuda was the first GPU language and the G80 architecture. So you can't. It's not just a language issue. The hardware need to support pointers, right? If not, it's a nightmare for you to imitate pointers in the software stack. Yeah.
Programming model and the execution needs to match the execution
Exactly,
model.
needs to
Right?
match. So
Yeah.
NVIDIA's G80 architecture that they launched in 2007, and with the Cuda, which is the first GPU language with pointer support, was the game changer, because for people coming from non-graphics world, from kind of CPU, regular programming world, it became like, hey, you can program in C, right?
Right.
Kind of, right? And so you still need to pack your work differently than writing a for loop in C, right? These thread groups and these concepts like that. But it was very simple to teach somebody that is coming from C world, how to take a simple for loop and annotate it to a CUDA program, right? And so that was kind of, the credit to NVIDIA. And you couldn't have done that with just a programming language. You need the GPU to match, right? That, right? So, so that kind of, CUDA happened in that time frame. But even then, right, from 2007 till 2012 or even 2013 timeframe, 6 years, CUDA was a solution looking for a problem, right? That, hey, it didn't really make much money to NVIDIA, right? They won some HPC contracts and supercomputer accelerator stuff. But it was like in the 100 million maximum range of revenues they had, right? It wasn't enough to justify like all the investment that was going on around CUDA, and that's another story for another time. I was very closely involved with them because I was at Apple. I was their customer, right? NVIDIA's customer, so was working very closely with them on variety of stuff. So that was one thing. The second problem with GPU or any accelerator stuff that the classic software people had was, see, you had to, again, using the train analogy, see, I need to move data into the GPU first before I can execute a program on it, right? And then this data need to move across the PCIe bus, right? I need to load the GPU up first, and then, like, say, go, right? And the initial complaint we got from people, this is great as long as, like, theoretically, once I load the GPU up and I dispatch computation, it runs fast. But, I have to pay for the loading cost and then the unloading cost too, right? I have to bring it back because the main loop is sitting on the CPU. And so while theoretically, right, you can show micro benchmarks doing great, macro level, it is not that big win, right? Moving data back and forth. So they were kind of dragging their feet because, for you to fully utilize a GPU, it is exactly like, if you're committing yourself to traveling by train, right? you'll have an entire plan, right? Every day, like, how do you get to the train station? How you get on it? How you get off it, right? You have a plan. But these guys were like, hey, it's just like a typical Californian, right? I love my freedom with the car, right? So I can go anywhere. So there was a lot of resistance. So the first people that came and said, we found something, hey, productive, we can go actually ship a commercial product with it, are the simulation guys, right? Like, the DASA systems, the ANSYS guys, right?
Right.
ANSYS that got acquired recently. They were the first people in my
Ansys have been
recollection.
guests on Oxide and Friends.
Oh, I see. Yeah.
Yeah, we actually
Yeah.
we had a
Yeah.
we're Ansys definitely a partner of Oxide.
Yeah, yeah. So I remember a distinct conversation, and this is actually in the history of one of the lessons learned. I say, hey, if you're McDonald's, right, and somebody comes to your counter and orders a burger, okay, and they're very hungry, right? I want a burger and a milkshake and some fries, okay. Don't offer them, hey, I have something better for you. I have a salad which is more healthy for you. You should get this and all that stuff, right? As a business, you should never do that, right? If your customer wants a burger, give it to him, right? Or whoever it is. So in this time frame, it's really fascinating history because NVIDIA was only a discrete graphics company. They didn't have a CPU, right? All they could do was just keep building discrete graphics, which sit on PCIe bus, right? And keep doing things. AMD was in a bit of confused state at that point, right? It had discrete graphics. In fact, when ANSYS came to us, we had more memory bandwidth and more flops on the discrete graphics socket than NVIDIA did in that generation. But we said, hey, ANSYS, we're building this thing called an APU where we are integrating, this graphics blocks and CPU blocks into one die, with a unified memory subsystem.
Oh my God.
And you don't have to move any data and all this, like, stupid things. And you could have a like this, HSA programming model, right? This new programming model where this Cuda is like, so crappy. You don't really want to do that. We have something new coming up. And the ANSYS guy, I remember, like, I was 1 week back from Apple into AMD. I was just invited to the meeting. I was sitting, the guy is like, yeah, those are all great. Sounds great. That thing is 2 years away. We are telling you today, I can just, with your stupid discrete graphics and this whole PCIe, loading, we can still take advantage of it because, the matrices are large enough. And if I pipeline, like, the matrix load into the GPU, and compute and the next matrix load, okay, I can get full utilization of it. And all we need from you, and hold on to your kind of seats right now, what they wanted from AMD was, we need you to support Linux and Linux, your GPU on
Really?
Linux, and give us Linux drivers, and that's all we are asking you to do. And we said, no, discrete GPUs are for gaming, and for compute we have this APU thing coming up, and you should
no hamburgers, just salad.
Yeah.
Salad's better for you. And I got some great salad.
Yeah.
It's gonna. I'm still growing it out back. It's gonna be ready in a couple years, but it's gonna be primo.
No, yeah. And that was the big, the reason the deep learning didn't happen on AMD or in this stuff was actually, a lot related to AMD not having at least an OpenCL-like thing running on Linux. Okay. So
really
Linux was deprioritized for years and years and years. And, I got it back to some level of priority in 2015 to kind of, when the AI thing was and deep learning was taking off, right? You had to fix the foundations, plumbing. If you don't have Linux drivers, and these things take long, Bryan, right? I mean, doing a driver, if you don't have a good driver, good memory manager, good stuff, people think, oh, what the heck? You have millions of dollars, just hire people and all. Guess what? Driver programmers, system programmers and all, they don't grow on trees anymore. You can't just fight, no matter how much money you throw at them, right? They don't exist anymore, right? And there are very few good people who understand kernel level stuff. And, I know you guys very much appreciate it with what you do, right? And you find, like, pretty dumb, stupid things at BIOS level too, right? And the number of people who understand these things are either gray-haired or bald-headed, and retired, and and this
Well, when
stuff. So
you also have the
yeah,
consequences of like it is that's really interesting. I not really thought that the gaming, of course, it makes total sense that the gaming history of this was really guiding people towards a Windows only approach.
yeah,
And
yeah,
of
yeah,
course, like the folks that actually want to use this as a general programmable thing on the server side, are like, no, we're not using. Sorry,
yeah,
pal, we're using open source operating systems. We're not using
yeah.
a proprietary
By the way,
operating system.
Windows had a very weird problem with compute. Okay, it's very fascinating. I mean, we could have said, yeah, why don't you kind of ship it on Windows, right? And kind of do that, right? Windows had a very weird problem is that because Windows was a graphics, GUI operating system fundamentally, okay, and the GPU device also renders pixels, okay, so you can't take the GPU away
That's
for
right. It's
like
occupied.
no hundreds of seconds away, right? Doing a big long loop, it will throw that Windows timeout exception error and reboot the whole system, right? So you have to context switch it. Like you can only give like pockets of work that are less than some number of 100 milliseconds or something like that, right? So yeah, Windows wasn't very favorable, like server operating system for like doing GPU, right? And on Linux, yeah, we could just kind of tie up the GPU for minutes at a time without,
Right.
TDR or what it's called. Yeah,
Right.
the
With
stuff. So,
with the
yeah, these
cost of
are,
switching workloads makes it
yeah,
especially
yeah, yeah,
interesting
yeah,
there.
yeah, yeah. No, but like these things are all fixable, but the DNA matters a lot, right? I am a
Yeah.
fundamentally a UI oriented operator. And this is one of the reasons why, Linux and desktop on Linux are still, you know, something that hasn't been solved yet, right? Like, that you can live on, right? See,
Listen,
it's,
I will thank you to acknowledge that after some prolonged experimentation, I finally found a Linux audio configuration that allowed us to not be glitchy on this very podcast. But it was not a small amount of work, and it did occur to me that you're on a but that is really interesting. So the GPGPU folks are putting obviously pressure on this thing to be used in a more general purpose for, and NVIDIA just sounds like was accommodating of that a little bit
of course,
earlier.
and
Yeah,
for them, it's also they didn't have other options, right? Like that AMD had CPU, right? Like
yeah.
so people were doing other things. NVIDIA had to survive with selling as many discrete GPUs as they could. Okay, and then they ventured off into Tegra. They also like everybody believed that you have to get into mobile and all, right? That because then the days of discrete GPU were numbered, right? And but the AI and deep learning thing happened, and rest is history, of course, right? And and in fact, the problem with integration, Bryan, when you look back, right, integration is not scalable, right? Discrete is a lot more scalable, right? Because right now you
Yeah.
look at the DGX box, okay? So I have 2 CPUs and 8 GPUs, or now like NVL 72 GPUs or something like that, right? So you can independently scale your compute elements, right, based on the problem of the day. But if I integrated CPU and GPU onto one die, right, you get the scaling ratio is fixed. You get
Yeah.
way too many CPU cores than you needed, right? And the stuff, right? I didn't need that. So, discrete has interesting property that you can scale the compute elements independent of each other.
It does, but then you do have this problem on especially on these LLM workloads, which are so memory intensive that now you are doing the fact that it's a discrete GPU, you are now doing a whole lot of work to get memory. As soon as you exceed kind of the HBM limitations
Limits.
on,
Yeah. See
you're
that?
hitting the
Yeah.
network,
Yep.
and and that's kind of where
Yep.
these
Yep.
because we're kind of in a nutty spot with this, or especially with respect to the
Yeah.
power
Yeah.
that
Yeah.
these things draw. I mean, I think
But I don't really need a bunch of CPU cores to solve or to increase my memory capacity, right? So the
Sure.
equation
Yeah.
that I put out on Twitter over the weekend, right? I said the performance equation, the numerator has become a function of flops, bandwidth, and capacity, right? And by capacity I mean memory capacity, right? And by bandwidth I mean memory bandwidth. But again, the bandwidth and capacity, you have hierarchies, right? You have your all the way from your register to L1s to L2s to HBM to LPDDR that might be connected across the bus on the CPU side to NVLink to Ethernet to your storage, right? NVMe or whatever, right? Each hierarchy has different capacity and different bandwidth, right? And so you're managing your data through all these levels of hierarchy, right? And so that problem is actually common no matter how you integrate CPU and GPU, is what I learned, right? Yes, it looks easier, if I am on a unified memory architecture, right?
Yeah.
Intuitively it feels easier, but
It does feel
for
easier.
attaining performance, yeah, but for attaining performance, I'm dealing with NUMA, right? Large scale NUMA, right? So you have to, I jokingly say the new UMA is NUMA, right? And
Right.
you know, so yeah, NUMA is here to stay, and um, there's no escaping it, unfortunately.
So another thing that you mentioned in that piece that I know, and I've talked about this in the past as well, is the role of packaging in all this.
Hmm.
And I mean, and you'd kind of had a note that like, boy, if I go back to myself, 10 years ago and explain how important the fact that packaging has become so important.
Yeah,
Could you elaborate on that a little bit
yeah,
and why packaging is so important and how it drives cost as well? Because I mean, I think that's one of your
yeah, yeah, yeah. No, so the basically, the end of kind of Moore's law, Dennard scaling, and all, right? So your opportunity. So now you're looking at system level opportunities to deliver more performance. So one of the talks I used to give, when I was at Intel to the both inside and outside is I used to call it what is the essence of Moore's law, right? So the the kind of the what you call the literal Moore's law statement was every 18 months you double the transistor density, right? Uh, something like that. But the essence of Moore's law was every 18 months or so you're providing double performance, double value to the user, right? At the same price or whatever stuff, right? So once Moore's law kind of ended, what are the opportunities for you to kind of keep the industry going by providing that increase in performance, right, at a similar power and similar cost? So all your optimization opportunities have become, I call it picojoules per bit optimization. Okay, so you have picojoules per flop, and power is the grand unifying limiter for all of us, right? Power thermals and all. You have how many ops can you do, right? How many picojoules for an operation, and how many picojoules for a bit, transferring a bit or moving a bit. So the picojoules per op is primarily controlled by my transistor, right? Which slowed down. I was only getting to a 10%, 20% improvement generation to generation. But picojoules per bit got 10x, maybe 100x in some cases opportunity, right? So integration, what was integration doing? Let's say I had, if you remember old motherboards, even a PC motherboard, right? I had CPU, South Bridge, North Bridge,
right.
right? And
Yeah.
memory. So,
Yeah.
and the South Bridge and the central CPU were talking through the motherboard interfaces and all, right? So they're going through analog SerDes and some tens of picojoules per bit interfaces to talk to the other guy. And when I brought
Yeah.
the South Bridge and North Bridge onto the same die, I took 10 picojoules per bit or higher, picojoules per bit interface, and made it into on die interface, which are like 0.5 picojoules per bit, right? 10x reduction. So that's another kind of way to look at why integration was necessary, right? Is to get the energy efficiency of all this stuff. So, so in that realm, but then now I can't, I still have limits on how big a die I can do, right? Like in the stuff, right? I have reticle limits and all. So to continue that integration packaging, so if I can put two dice together next to each other and they can talk, low picojoules per bit, high bandwidth, I have the same benefits of integration without making a big monolithic die, right? That was the genesis of advanced packaging, right? How can I stitch two dice together at a very low picojoules per bit interface and high bandwidth, so that I am mimicking a big, large, monolithic integrated die. So that's one. That's in the 2 dimensions. Now imagine 3 dimensions. So if I stack the die on top of each other, right? The distance, by the way, the picojoules per bit is the energy is also proportional to the distance the bit needs to travel. So even in 2D, if I have to travel long distances, I'm consuming, a lot of femtojoules per, I forget the exact number on how many femtojoules per, nanometer. I referenced Bill Daly's talk in my Twitter thread.
Oh, that's such a good talk. I love that talk.
He lists that femtojoules per, nanometer in the talk. You can compute. But when I put 3D stacking, I'm kind of cheating, right? Cheating in the sense it's a cool optimization. I reduce the distance, how long the signal needs to travel. So that kind of, made the 3D packaging very interesting, right? So both the 2D advanced packaging and 3D packaging are mechanisms or tools for me to reduce the, the picojoules per bit while delivering more bits, right? Delivering more bandwidth. So that was, the why those tools were important and why we were working on these tools for a long time. And I was, I call it my early scars on the back. Like if you're the first guy to use a new tool, you pay for a lot, right? You pay for everybody's learning and the cost.
And this was at AMD, right? I mean,
at AMD, I did. Yeah, we did the Fiji HBM1 on a GPU. The first HBM GPU was done by AMD, right? So we had to, plumb the entire, roads for it and, and discovered a lot of things. But so now coming to the cost, right? So there are two aspects of this cost always, right? One is until a particular technology and a manufacturing methodology scales, okay, to high volume, all the initial capex that you put, right, capital expenditure you put, is amortized on these chips, right? So you end up paying, big money whenever you come up with a new technology, which may be awesome physics-wise and all the stuff, but there is an upfront cost to it that gets, somebody has to pay, and the early adopters end up paying, lion's share of that cost, right? So there's that cost aspect. The other cost aspect is time is cost, right? So, if a standard package took me, 1 hour to package a thing and test it and put it out, right? Whereas an advanced packaging took 7 or 8 hours, okay? The time in the fab also gets billed to you, right? Because time is money, right? That every second the dollars are ticking for on these factories. So you have to come up with methodologies where the amount of time it takes to package these advanced things is also lower. But since the whole advanced packaging is new, and let's say you look at an latest NVIDIA B200 package. Okay, you got 2 big dies and then 8 HBMs around or something like that, and then NVLink connection on the side. Its layout is very different than MI300 from AMD, and its layout is very different than Ponte Vecchio from Intel, right? It has got 47 tiles. So the automation in the assembly line for each of these packages is very different. So so you don't really get, whereas a standard package is automated, like, almost 15, 20 years ago, right? It's not very different. So, so that adds cost. So, it's a long-winded way of saying that there is the time it takes to assemble these packages is longer than the standard packages, and you pay. Okay. And the last cost is actually the physical material cost. Like may have an organic substrate and this and that and all that stuff. You have AMD has a big interposer underneath, which is a older generation silicon technology. So you have to pay for that wafer cost. So they all add up. And right now it's kind of pretty high compared to a standard packaging cost. But as I said in my Twitter note, not all of it is like, kind of physics justified, right? The cost. A lot of it is, a lot of it is because AI is in this big hype cycle and NVIDIA is making, 90% margins. Everybody's in the ecosystem says, hey, why am I not getting, some of it? And they jacked up prices. Everybody jacked up prices, right? And the stuff. It's just ridiculous right now that every component that's involved in building one of this, GPU type things with HBM is not is out of reach for regular stuff. And I think that's actually unsustainable because for AI to reach 7 billion people, it has to the infrastructure cost need to come down to kind of like the regular general purpose cloud costs are even lower, right? Frankly. And I'm optimistic that it's going to happen. I think this hype cycle need to kind of there'll be a crash for a little bit, where we don't need any more GPU. It's because if I want to build a 1 megawatt data center, Bryan, right now with NVIDIA hardware, it costs me $35 million. Okay, for 1 megawatt. Okay,
right.
Yeah,
and that's assuming that you can find the megawatt. I mean, there's a real power infrastructure problem here. I mean, this is the power problem is quite real.
That's interesting, right? It depends on regions, right? Like, so I'm working with a few entities in India that have, this big, gigawatt solar farms.
Okay. Well, there you go. Yeah, great. Okay.
Yeah. Gigawatt solar farms, and their daily wasted power is 100 megawatts because the grid.
Yeah, I was going to say they may have the other problem. They may have the problem that you had, back in the day of like, hey, we got to find a way to spend all these gigawatts coming off of the solar arrays.
Yeah. Because transmitting power is more expensive than transmitting bits, right? So actually, it makes a lot of sense that this data center should be co-located with this solar energy stuff, right? So I think there is still power left, but and that's an entire 2-hour episode on energy, oil, coal burning, and all that's happening in US. The oil power is still cheaper here than other alternative energy power, right? But that is, I think, more a US statement than rest of the world statement.
Well, and that's very interesting. Just about the cost of transporting that bit versus co-locating with the solar arrays. All right. So we've got the spare gigawatts, so we can just like co-locate them. But but these are still. I mean, as you point out, like just the cost from buying the chips, buying the DC. I mean, this is a very expensive capital outlay, and you do wonder. It's like, boy, is that the right? Does that make sense? Is that the right kind of economic distribution? Is that the right use of our scarce resources?
Yeah. I think we need to get it to $1 per watt, right? Or something like that, right? I think that's a good goal, right? $1 per watt. So that'll be $1 million for a megawatt, right? Versus 35, right?
Yeah, $1 per watt. So you mean like $1 per watt
capex,
capital
right?
cost?
Yeah, I'm saying. Capital cost should be $1. Compute capital cost should be $1 per watt.
Interesting.
Right.
Interesting. Yeah, that is that's aggressive, isn't it?
That's aggressive. I mean,
the math
but,
on it. I'm like, boy, that's going to be a big price break on an Oxide rack. Oh boy.
yeah. I think I don't know if we can do it with just the metal around these things, right? Forget
I
the
don't think
silicon.
I'm pretty sure that our investors just started throwing up in a trash can. But that's an interesting goal to kind of think about.
Yeah. No, by the way, I just came up with the goal right now. I didn't think about it. I just
thank
it
God.
sounds good, right? Dollar per watt.
Oh God, you made that up. Thank God. I was really concerned that was going to be the. I mean, it is interesting to think about though in terms of like, in order to be, right now we do have this kind of disproportionate amount of capex going to compute for this one use case around LLMs. And or at least there is a lot of froth and fervor around that. It's unclear how much of that is actually going to land. I do think that, like, in terms of, because Adam, this is something you and I have talked about many times over the years about the need to start thinking about our systems holistically in terms of hardware and software, and in terms of the actual watts of the kW of our workloads and or the megawatts of our workloads.
Right. But by the way, Brian, that reminds me, interesting segue, right? Is like. I recall, like, reading, right, that railroads were a big deal in 1920s here. Like, it's like everybody, like all the billionaires were railroad tycoons and all that stuff, right? It feels like that this big GPU infrastructure we're building might become the next railroad in America, right? And the stuff that, then once we build the highways and all, they gather dust, right? I mean, right now they are, largely used for this, slow Amtrak's for retirees, having time or something like that, right? Yeah.
Well, no, that's right. I mean, I think that there is, and certainly in the 19th century, fortunes were won and lost many times over in the railroads, and became it is interesting when you kind of think about how all that infrastructure. I mean, and Adam, I keep thinking back to the episode we had with Simon Willison. Where, and Raj, I don't know if you've listened to anything from Simon, he's extraordinary, but we talk because talking about the pressure on getting similar efficacy with much smaller models, and how like that will be really economically fruitful, and getting some of these sizes down a little bit, which would I think just take some of this pressure off. Because I think it is bad for humanity. I think, Raj, as you were kind of saying, that when these things are so expensive and so unobtainable, that is not sustainable in a way that's kind of not good for the future. You want, like, that there's going to be the future compute use cases are going to be made because someone's got these elements in front of them they can experiment with in a way. And we don't want that to only be via a megawatt, even if that's only $1 million in your in Russia world. But we want to have ways for people to experiment with this stuff. Well,
I mean, if you take inspiration from a mobile computing right now, right? I mean, if you just look at, right, even an Apple M1, for example, right? We know the cost of it, we know the energy efficiency of it, and all that stuff, right? I mean, I did this math before, right? You scale up a mobile computing element, right, to a megawatt scale. It's what we recall is it's at least the order. It's like 5 to 10x better than a H100 or a B100 or a Sapphire Rapids type stuff, right? So we have existence proof that we could that there are this highly energy efficient things in the mobile world, and kind of highly energy inefficient things in the server world right now, right? And I think my bet is the disruption is going to come from scaling up from the mobile world, and whether that happens, and I think the small models and other stuff is an orthogonal element there. But just design principles wise, right? Like that these things are unnecessary. I mean, there's so much low hanging fruit, energy efficiency and cost efficiency sitting on this big honking things.
It's a great prediction. Just that's sort of where NVIDIA and had disrupted folks like SGI back in the day. So
Get
that power and volume. Yeah,
it comes from small, right? The the small stuff, and we see that actually. If Apple was not was a silicon company, right, is shipping chips,
Right.
right, it would be a different discussion altogether, right? Yeah. Put a whole bunch of M1s or M3 Ultras, right? Rip apart from a Mac Mini or Mac Studio. And you can do the calculation, right? Like, less than 80 watts, they have 192 gig, 1 terabyte per second, right? Infrastructure. Okay. So, 192 gigs is how much memory does that B200 has.
Right.
Right. And you can, it's LPDDR. So, they ganged up to get 1 terabyte per second, but you could see that there's a path to 2, maybe 4 with low power interfaces right there. Right. 80 watts versus, 1 kilowatt.
Versus 1 kilowatt.
Actually.
Yeah.
Yeah. In fact, that's the other kind of stuff that I was doing, doing this math, right? NVIDIA claims 2 petaflops, right? It's 0.7 picojoules per bit, per flop. So 2 petaflops would consume 1400 watts just for flops. So the TDP specs that they give are assuming that you're, less than 50% duty cycle on your compute, right?
Yeah.
Right. So if you actually turn on all the flops, you don't have enough power on those sockets, right? So you needed 2 kilowatts for to run it at its full glory.
Crazy.
Yeah, it's crazy, right? One chip, burning so much. So
burning so much. Yeah, you're right. And it's got to be, and so the disruption happening on the efficiency side of this. Well, just to your point that you started earlier, but in terms of like, once these things have, there's going to be some settling that's going to happen around efficiency and cost, and that has not happened right now on the GPUs right now, where it's just kind of all drags.
Yeah. And that's going to I mean, it's the opportunity is, definitely the dollars are there now, right? And
absolutely.
right. So I think, it's the question of who and when, as I always say, right? It's not a question of if, it's who and when.
That's right. Well, and Rush, I just love also, I mean, there's so much to, I think, to learn here for folks that are, especially folks that are earlier in their career, honestly, about having seen so many boom and bust cycles. And the booms were always a little exuberant. But I also think that, something that your experience tells us is that the busts were overly pessimistic. And, ultimately, there was a new kind of revolution that would come along and would find ways to use these things in different ways.
Yeah.
And that has kind of been, I mean, that change is the kind of ever-present constant here. Which makes it,
the amazing thing though, right? I mean, again, for, those in this, the nerds in this space and like, the enthusiasts and all that stuff, is it's just amazing that, the 30 years I've been, right? That performance and performance efficiency, right? When I say performance, not just absolute, right? Performance in a given constraint, right? Given power constraint, cost constraint and all, is one constant theme, right? It never went old, right? That, right? It's just, keep giving me more performance within certain, constraints. And there is always a market, right? A friend of mine who worked at Apple, Dave Conroy is his name, amazing guy. Like he made this statement once at Apple when we were debating, when somebody was like, he said, hey, why do we need to put more CPU, more GPU, right? Everything runs great on an iPhone 4 or iPhone 5. I remember in the stuff, right? It's like, we already had Angry Birds, right? So you remember the game Angry Birds? It's
the
like,
peak of civilization.
Who wants more graphics than this stuff? This is like the most like, compelling game and everybody's playing. What do you want to do within this stuff? And Dave looked at that room and he said, like in the history of computing, anyone who bet against performance died. Right? I remember that statement. And don't ask why do you need more performance. Ask the question why not. Right? So he just said, like, don't, if you can do more performance, do it. But within the constraints, right?
Within the constraints. I was going to say, not at any price. And it's like and right now we are at performance at a high capex
Yeah.
price and a high power price. And
I just, by the way, fascinating, just funny story. I just came back from China. Okay. I went there after 5 years. Okay. So, how, there are all the sanctions going on against China and all, right? And then NVIDIA had to do this lower spec
right,
H100, right, to go to China
right,
and all. And they didn't actually reduce the price on it, right? It's just lower spec H100. And the fascinating
okay,
thing is because it's lower spec, I need more of them to run the same model,
huh?
right? Okay, so it actually boosted their sales, right, to crazy
Oh my
in
God.
China, right, in the stuff because I need more, right, of the stuff. It's just perverse, but it's just I was just laughing at the show. It's like, wait, you're buying more,
Buy
right?
more, right? I don't think that had the intent that. Yeah, exactly. I think it
And
had
the
some
stuff.
unintended side effects. Well, I mean,
Yeah.
good for Nvidia, I guess.
Yeah,
But
yeah, it's great. Yeah, they landed on inside this, beautiful thing where, the less utilized it is, the more you need to buy, right? So yeah, they landed on a problem that is low utilization per GPU, but it still scales with the number of GPUs, right? It's just awesome, right?
boy, it's good to good to be the king, I guess. But
Yeah,
I think we can fully expect that, as just as you said, like these things are, we can fully expect that to change, and this is going to be, and I would also add, actually, it's funny you mentioned Angry Birds. I just love the fact that, I mean, I really, like, I am almost certain my 12-year-old daughter has never heard of Angry Birds. I know my older boys, I know the 19-year-old and the 17-year-old have. I don't think the 12-year-old has. So I just love the idea that, like, Angry Birds kind of capturing this total moment in time.
right.
And I also think, another thing that's very funny about Angry Birds is that in Mark Andreessen's piece, Software's Eating the World in 2011, and that piece, by the way, and I know he's hailed as a prophet because of that piece, which is kind
Mhm,
of ridiculous because it's like, great, software's relevant, fine,
mhm.
but the software's important. Okay, I guess that was a breakthrough in 2011. The actual companies that he cites includes Rovio.
Yeah.
Rovio is going to be one of the new kings. Rovio, the maker of Angry Birds,
Mhm.
and it's going to be Rovio, and it's going to be Living Social, and it's going to be Groupon, and it's going to be Foursquare. Those are literally the companies that he names in that piece, and does not name Nvidia or
Yeah.
AMD and I think what's interesting is Nvidia. I mean, just you mentioned this earlier, that Nvidia really understood that the software hardware co-design, and Nvidia is very much a software company in addition to a hardware
Yeah.
company. And I think that the future still lies at that interface. That interface remains a very important interface, and I think that people should not, don't let anyone tell you that there's no innovation to be had at the hardware software interface, because Raj, I'm sure
Yeah.
you'd agree that
Yeah. Yeah.
remains a very rich vein.
No,
It
no,
remains
it's a hugely rich thing, and also because I think that's why I firm believer that there is a disruption in front of us, right? Because the most dominant kind of programming abstraction became Python and its associated libraries, right? And I keep kind of the last year I've been digging into it because um, I think what is the future, right? I mean, there's so much. It is Python, and for us hardware guys, our notion of abstraction stopped at C++, right?
right.
So yeah, so there's definitely I think that's my bet that somebody is going to come from the Python side of the world, and Python and memory are what I call the marriage of Python and memory is could be where the next disruption comes from.
Interesting. Andrew, well, this has been a great conversation. Raja, thank you so much. This is I came in with high expectations and you over delivered. I love the analogies. I think we more than answered the question, and I think given folks a lot to think about in terms of the past and present and future of heterogeneous computing. And if nothing else, hopefully folks, I mean, Raj, part of the reason I love talking with you is because you and I share, and Adam, a real excitement for not only where we've been, but where we're going. And there's a lot that's still possible out there, which is what makes it interesting and exciting.
Yep. Thank you. Thank you for having me. It's always fun to nerd out on this topic. No
It is
effort.
always
Yeah,
fun to
yeah,
nerd out. It is
yeah,
always fun
yeah.
to nerd out. And well, again, thank you very much. Really, really appreciate it. And I think we've teed up like a couple more in-depth episodes we're gonna have to have you back for. So this will not be the last for sure. But thank you very much for joining us.
Yeah.
A lot of fun. And for listeners, if you got other ideas that you want to hear, please let us know, because we love the requests. And you can complain about the audio problems too, but those we're gonna ignore. But the lack of intro music. All right. Well, thanks everyone. Thanks, Adam. Thanks again, Raja.